hear me?
Yes.
Okay. First of all, thanks a lot for the organizers for organizing this lovely meeting. Always great to be in Taipei, and also thanks for inviting me. So today I want to talk about some novel techniques that are probably new for a lot of you in this audience. So first of all, this question was asked yesterday in the discussion session: what is a galaxy proto cluster? I think in the abstract, most of us will agree we want a galaxy proto cluster to be defined as something that will eventually become a massive galaxy cluster at redshift 0. So something that might end up as 10 to the 14 halo mass or above. And then the question is, well, how do you actually detect them, and how do you, define them as a proto cluster within the observation? So we heard about various techniques. TSZ, X-rays if there's already hot gas, and various kinds of overdensities of galaxies in various multi-wavelength observations. I'm going to mention about also lambda alpha Flores absorption, which is something relatively new within the past decade. But one thing that's common is that you do need these studies to be connected to the redshift 0 population of clusters in order to have any meaning. So, so typically, what would you do in your analysis? You have your data, some observations, and then you see in the observations, well, there's some overdensity. So you pick some aperture. It could be a radial aperture, it could be some nearest neighbors, etc. You say, okay, so this is some sigma overdensity of galaxies, and then you go into Millennium simulation and say, oh, look, there's a similar sigma of overdensities. This is going to end up as 10 to the 15 cluster at redshift 0. Therefore, we have found my redshift whatever coma cluster progenitor. Done. So there's a study from 2013 that is not so well known by Chateau et al. They kind of look at this issue in more detail. So they look at n-body simulations and the fact that we've already heard that proto clusters at high redshift are extended objects. And they're also not spherical extended objects. They have asymmetries, they're fed by filaments. And so they looked at the question, well, if you're using fixed apertures or n nearest neighbors, how well does this density calibration work? So this plot shows a sequence of kind of the overdensities, the true overdensity in 3D versus the overdensity you measure in your aperture or nearest neighbors. And this is a sequence in increasing density of tracers. So, well, if you have an extremely high density of tracers, then you're doing fine. You're recovering the overdensities as you expect, and this starts falling down as your sample gets sparser. And this is for the case where you know the exact redshift for all your tracers. When you have only, say, photometric redshift information, this gets significantly worse. So even with high density of tracers, you need to be very careful about calibrating your apertures with what you actually observe. And this is in the case where you have perfect knowledge of the mapping between your n-body simulation or simulation with your tracer. So you need to know exactly how to make galaxies in that simulation to exactly match your observations. So this would be the ideal case. Another issue is that, so Yi Kwan wrote his seminal paper 12 years ago now, where again, we know that proto clusters are extended overdensities over tens of megaparsecs. And so, when you look at n-body simulation and for example, you look for the most massive halos at redshift 3 or 4 or whatever, they are not going to follow monotonic tracks in terms of how relatively massive they are at a time. So in this plot, for example, these are kind of the most massive halos at high redshift, and they kind of move around. So for example, one of the most massive halos at redshift 0, if you extrapolate, if you track it back to high redshift, it's not a remarkable halo at high redshift. So if you find something that say, oh wow, this is a really massive halo at redshift whatever, there's no real guarantee that it's really going to end up as a massive cluster. So I put this phrase in my title, and not all of you know what this is. So what is field level inference? So in your traditional observations, what you do is that you have You make your observations, could be photometric, could be spectroscopic, in whatever wavelength, and then you compute some summary statistic. You compute power spectra, you compute luminosity functions, mass functions, whatever, and then you go into your simulations, you compute the same things, and see whether they agree, right? So that is kind of a traditional way. Field level inference skips all this. Field level inference says, I want my simulation to simulate exactly what my observations show me, given going through some forward model. So I'm going to show some examples. And so this is not a completely new technique. It's been around for 10, 15 years now, but the previous applications have mostly been to reconstructions of the local universe from, say, Sloan Digital Sky Survey. The high redshift is an interesting regime to try and apply this, because first of all, well, the less time has passed since the Big Bang, and you're at high redshift. And secondly, the structures they are interested in, especially things like protoclusters that are maybe 10 megaparsecs, are basically in a nonlinear regime, so the physics are a little bit easier to track. And the next generation of spectroscopic surveys are really starting to probe this regime, so it's an interesting epoch. So it's been a couple of years now that my former postdoc Metin carried out this study on the Cosmos field, where he first compiled all the spectroscopic redshifts he could get his hands on, so include surveys like Z-Cosmos Deep and VUDS. And the goal was to try and reconstruct the 3D density field represented by this sample of redshift 2.5 galaxies. So the methodology was to basically use Hamiltonian Monte Carlo sampling to try and solve for the best fit initial density fields driven by 12BT as a forward model for the gravitational evolution. So this kind of shows the schematic where you have the bin galaxy density from the redshift survey, and then this is the Lagrangian initial conditions that will eventually evolve to match this. So 2LPT is kind of like second order beyond Soldovich theory for gravitational evolution. And then the next, that was in the first paper. In the second paper, we put this into an N-body code to generate the full cosmic evolution. So again, step one was just a reverse reconstruction run using 2LPT. And then we also use a forward run where we took those initial conditions, and of course we evolved it to our observed redshift at 2.5, and then ran forward beyond what the observations show. So let me illustrate. So this is the 3D distribution of the spectroscopic galaxies that we had in this Cosmos field from redshift 2 to 2.5. So a degree is about 60 to 70 megaparsecs on the side in the transverse plane. And you can see the 3D structures here. And then, so he solved for the initial conditions. So these are the density field that is consistent with the observations of redshift 0. Now we're zooming into this Z-Fire protocluster at 2.11. And you see now the time stamp has moved beyond the time stamp that we actually observed these galaxies. So we can see that the structures represented by the redshift 2.1 galaxies that we see will indeed collapse into something like a 10 to the 15 solar mass halo. So not only do we have one simulation, because the Hamiltonian Monte Carlo does give us posterior realization, we're actually able to run something like 50 N-body runs, similar to the one that I just showed. And given those, we can actually make statistics for how often does this blob here end up as a given redshift 0 halo. So we have error bars on the formation of these redshift 0 clusters, and also probabilities. So one of the most interesting structures in Cosmos is this so-called Hyperion supercluster. There was first, there are multiple observations by various groups that kind of found interesting structures, and Pucciati and all kind of synergized this and say this is all one big structure. So in our analysis, we found that it consistently forms a a filamentary supercluster about 100 megaparsecs in length by around redshift 0. So there's a couple of redshift 0 analogs. One of them is called this coma A1367 filament that connects coma and ABL1367. So it's kind of interesting that we're able to see progenitors of such protoclusters and model them in detail at high redshift. So within this analysis, of course, Cosmos is an extremely well-studied field. We were still able to pull out several new protoclusters that have not been published within this, the central pointing of Cosmos. And we found candidates that are down to redshift 0 masses of around a few times 10 to the 14. So, for once, we are not claiming these are coma cluster progenitors. We're saying we can actually push down to kind of more run-of-the-mill clusters and progenitors. Another technique that I pioneered to look for over densities at high redshift is so-called laminar phosphorus tomography. So this is basically exploiting the laminar phosphorus. So I've heard about this in class where you have this distant quasar. The absorption lines in the trace amounts of neutral hydrogen gets imprinted on the quasar spectrum as it redshifts, and so you have kind of this barcode of density fluctuations in your spectrum. So you are probably aware that traditionally this was using quasars as your tracer, and this gas has some mapping to the underlying density field. So this forest is a probe of the underlying density field. So again, traditionally quasars were used as background sources, but it was pointed out that if you have sources that are much more densely packed on the sky, so one sightline will give you some one-dimensional information, but if you have multiple tracers that probe a given sightline, you can start reconstructing the 3D density field traced by this absorption. And each path in this, the path represented by each sightline is several hundred megaparsecs. So this actually represents efficiency boost in probing large-scale structure and redshift 3. So it's been over 10 years now that I've been leading this Clamato survey. That was a pilot survey of the KEC. That covered the central region of Cosmos field, or something like equivalent to a third of a square degree. And so, so I'm not going to talk so much about it, except to say that we pioneered the detection of overdensities that we think are consistent with protoclusters about 10 years ago. It was actually the main driver to develop this technique. So this is actually that Hyperion structure that I talked about that we detected in this laminar phosphorus absorption about 10 years ago now. Since then, I think there are now something like 50 known protoclusters that have been, I think it's about 30 known protoclusters that have been discovered by the successor survey led by Newman et al. Called Lattice. So I think this is a field that's continuing to grow. When I showed the movie just now, that was the density reconstruction of the spectroscopic galaxy sample. We can also try and do reconstructions using the laminar phosphorus data. So this was developed by my collaborator Ben Horowitz, who was at the time a grad student, is now a postdoc at IBMU. And the problem is a little bit different, so we had to develop different codes where your galaxy survey is a sample of zero-dimensional discrete points, whereas this laminar phosphorus are 1D skewers that probe the continuous field. So I'll not skip this. The approach is a bit different, but again, it's driven by fast n-body methods to try and evolve the density field very quickly, and then we apply some sort of approximation to map the density to the absorption, and then compare that with the actual data, and then kind of iterate to try and solve the best fit initial conditions. So this movie kind of illustrates how this goes. So this is showing one example sideline where the blue is the true data, and then the dotted is actually the kind of noisy version, and it's just one sideline out of like 1,000 going through this box. And over something like 100 iterations, it tries to converge to the true absorption. So there's some small scale power that's missing, but overall it's a decent reconstruction on megaparsec scales. So this code, which we call TARDIS, is basically also gives us the underlying density field, and because it does, it tries and draw a Gaussian lambda CDM density field at each iteration. The field that comes out is the lambda CDM density field. So basically, what happens is that in traditional, say, linear filtering methods, kind of like the field can be unphysical in terms of large-scale structure, but in this case, it is forced to be a lambda CDM field, and so we kind of have information about the cosmic web that might not be immediately obvious. So this is an example that shows a linear filtered flux that kind of looks a little bit more Gaussian and blobby. And once we pass it through this TARDIS, we can define filaments that are likely to be there because of large-scale structure. Of course, we have the initial conditions in this volume, and so one of the things we did in collaboration with Dylan, who's also here, was to stick that into a hydro simulation. So this is a project that we call Cosmos TNG, led by a former postdoc at Heidelberg, who is now about to move to Stanford, I think. So this is a plot that is, I think, is the first time someone ever put a simulation together with observations. Basically, this Cosmos TNG covers the same footprint as Tamako, so that's easy. And the first paper focuses on this Z11 protocluster, this Zephyr protocluster at Z of 2.1. So this is the hydro box. So you can already see this is the density field that's run on the n-body run. And we did full hydro here. The dots are the spectroscopic galaxies that we see in this volume. So as I mentioned, this TARDIS method only reconstructs density field down to about 1 megaparsec scales, which is obviously too coarse to stick into a hydro simulation that goes down to at least 100 kbc. So we had to artificially inject power into scales smaller than this. So this shows the blue power spectrum here shows what comes out of the constraint realizations, and we had to inject some random power to kind of make it look more like a lambda CDM power spectrum. And so basically, Chris ran 8 variations where there were different realizations of this small scale power. And so this kind of shows kind of a snapshot of one of the overdensities in the field, where it turns out things were actually reasonably consistent for this. So things like the star formation rate density were consistent to around 10%. The numbers of galaxies in that whole volume didn't change much, and the most massive cluster within this Zephyr protocluster was also consistent within about 20% or so. Of course, we have to show a video. So this is the kind of complex of nodes that at redshift 2.1 will eventually be collapsing into a massive cluster at redshift 0. And again, this is representing the actual observational field. So we've only just published this first paper earlier this year. And one of the things that are really striking is that when we compare the filamentary structure in that simulation, some of the triangles and the circles here are actual observed galaxies in the cosmos, and these were not included in the reconstruction, right? So you can see that the distribution of the galaxies are following the filaments in the simulations remarkably well, even though they were not included in the sample. So this is really exciting, and we're going to explore how to exploit this in the future. So there are next generation things that are happening. There are advances in parallel GPU computing and also sampling methods. So my student Chen Zedong is basically developing a n-body-based method that can generate this kind of reconstructions in about 50 times faster than previous methods. So the kind of paradigm that we're working with now is that we have some fast approximate method as the forward model to try and derive the initial conditions, and then we stock those initial conditions into Hydro to generate Cosmos TNG. I think in about 10 years' time, we might be able to do the full Hydro field level inference, where the whole everything is included in just the sampler. So this is kind of a prototype differential Hydro sampler by Ben Horowitz that shows kind of a volume that runs baryons and dark matter with a very simplified with a very simplified subgrid feedback model. And this is a fully differential code. So there's a huge amount of work to actually make this a real Hydro code, but the beginnings are there. I think last 1 or 2 minutes I want to talk about PFS. We've already heard about this. There's a massively multiplex fiber object spectrograph that's on Subaru. We've already, in fact, I'm a survey coordinator and we're observing it now, so I'm pretty busy. And I'm one of the co-chairs of the Galaxy Evolution Survey that has multiple target classes going out to Redshift 7 over about 10, 12 square degrees in footprint. And the last point I want to make is that the footprint that we're covering with PFS, like we call this the Galaxy Evolution Survey, and cosmologists will say, well, this is not cosmological volume, but it turns out the footprint is equivalent to what we call cosmological volumes in Hydro simulation. So so that kind of drives why we're doing this, because we're exquisitely sampling this particular volume on scales that should be achievable by state-of-the-art Hydro simulations. So I think, again, just to show you this beautiful spectrum that we have from the first few days of observations. These are LBG at Redshift 2.8 it's a bit bright, but the signal noise looks really good. And yeah, the observations are ongoing. And I'll just leave out my summary slides. Thank you.
Okay, time for questions. Yeah.
Thank you. I'm not sure if I understand this correctly, but you reconstructed the density field at Redshift 2. And since Cosmos is such a well-studied field, there must be tons of data at Redshift 7. So if you rewind your reconstruction back to Redshift 7, can you match what's observed at the time?
No, because it's a different part of the light cone. I mean, we're seeing a light cone that's... So in this business, we have the confusion of Redshift as a timestamp and Redshift as a distance indicator. So when I say Redshift 2 in Cosmos, that's a distance, that's kind of a coordinate, right? And then when I say we go to Redshift 100 and 0, that's the time. So we're at that part of the cosmic volume, we're rewinding it in time. So it's a different view, yeah.
Okay, another question. Oh, yeah.
Thank you. First, very interesting talk. I really enjoyed it. I had a question, kind of a follow-up to what Yunting was asking, which was, in order for using Costco to constrain the realizations, what is your data requirement? Because Cosmos is obviously one of the best fields out there. I'm just trying to get a sense of how more broadly this could be applied.
Right. So this was kind of the legacy of Cosmos, right? 10 years of
Right.
big telescope observations, and this was a few thousand galaxies over 1 square degree. And so this, we think it's good to scales of protoclusters. So I think we are resolving with 5 megaparsec scales. That's decent for studying protoclusters. And and then to link back to my talk about PFS, PFS will get this number density at this redshift over 10 times bigger footprint.
Thank you.
Okay, let's thank KG again. Thank you.